Hi Year 12, this is the second video for the solutions to the 2022 Extension 2 HSC paper. In this video we're going to look at questions 11 to 13. Right, here's 11a. Express 3 minus I divided by 2 plus I in the form x plus iy, where x and y are real numbers. Okay, nice easy one to start with. So we're going to multiply by the conjugate, aren't we? Which of course is 2 minus I is equal to, now I'm going to just expand these top brackets, 2 3s is 6, take away 3i, take away 2i, take away 1, all over, and now expanding these brackets, which of course is the difference of 2 squares. 2 squared is 4, take away negative 1 is plus 1. And tidying it up, we have got 5, take away 5i, all over 5, which is 1 take away I. 11b, evaluate the integral of sine cubed 2x cos 2x dx. So I'm looking for a reverse chain rule here where I've got the derivative of the inside function sitting there, and I mostly have that with this cos 2x. I'm actually going to do a substitution. It'll make things a little bit easier. Let u equal sine 2x. du dx is equal to 2 cos 2x. And so du is equal to 2 cos 2x dx. All right, let's substitute. Integral. So sine cubed 2x is u cubed. And then cos 2x dx is du on 2. Let's integrate. A half. Then I've got u to the power of 4 over 4 plus c. Substitute back in. I have 1/8. U to the power of 4 is sine to the power of 4 2x plus c. 11c. Write the complex number negative root 3 plus I in exponential form. So in the form r equals I theta. R, of course, is equal to the square root of negative root 3 all squared plus 1 squared, which is 2. And then tan theta will be equal to this number here, 1 over negative root 3. Now I'm going to have a quick look and see which quadrant this is in. So we've got negative root 3 plus I, it's up here. So theta, if I think about inverse tan, let's write this over here, of 1 on root 3, well, that's equal to 30 degrees, so pi on 6. And in this quadrant here, it would be 5 pi on 6. And so, in exponential form, negative root 3 plus I will equal 2 e to the 5 pi on 6i. Part 2, hence find the exact value of negative root 3 plus I to the power of 10, giving your answer in the form x plus iy. So let's take exponential form and raise it to the power of 10. 2 to the power of 10 is 1024. E to the 50 pi on 6i, which is the same as 1024. E to the 25 pi on 3i. Now 25 pi on 3 is way too big. It's greater than pi, so we just subtract 2 pi over and over again. In fact, I've got to do it 3 times until I get back into the domain. And that will give me pi on 3, which I'm happy with. So it equals 1024 e to the pi on 3i. Now this is equal to cos pi on 3 plus I sine pi on 3 equals 1024. Cos pi on 3, that's cos 60, that's a half, plus sine 60 is root 3 on 2, equals 512 plus 512 root 3i. Question 11d. A triangle is formed in 3-dimensional space with vertices A, B, and C. Find the size of angle ABC, giving your answer to the nearest degree. So we know A has coordinates 1, negative 1, and 2. B has coordinates 0, 2, negative 1, and C has coordinates 2, 1, 1. Now, of course, we want to use this formula. Cos theta is equal to, let's call this vector A, dot, and this can be vector B, divided by the magnitude of A times the magnitude of B. All right, we need to form these vectors. So vector A will be, A, so 1 take away 0, -1 take 2, and 2 take away -1 is 3. And then B is going to be 2 take 0, 1 take 2, 1 take -1. All right, so this is equal to dot product 1 times 2 is 2, plus 3 plus 6 divided by the square root of, what have we got, 1 plus 9 plus 9, and square root here of 4 plus 1 plus 4. Now putting that into the calculator, we get 0.841, and theta will be inverse cos of 0.841, which is 33 degrees. 11e, let L1 be the line with this equation here. L2 passes through the point A and is parallel to L1, so it's going to have the same direction vector. Find the equation of L2 in this form. Okay, so we can write it like this. xy is equal to, it's going to pass through this point, -6, 5, and it's going to have the same direction vector. I'm going to use t, I want to use lambda, the same. 3, 2. And now we need to change it to put in this form. So x is equal to -6 plus 3t. Y is equal to 5 plus 2t. Make t the subject. 3t is equal to x plus 6. T is equal to x plus 6 over 3. Substitute in. Y is equal to 5 plus 2 lots of x plus 6 on 3. Up here, y is equal to 5 plus 2x on 3 plus 4, I think it is. And so y is going to be equal to 2x on 3 plus 9. 11f, use the substitution t is equal to tan x on 2 to find this integral. So we know that cos of x will be 1 minus t squared over 1 plus t squared, and sine x will be 2t over 1 plus t squared, and dx will equal 2 on 1 plus t squared dt. Remember, this one is not given for you on the reference sheet. Substituting in, we get a mess. 1 plus 2t, no, pay attention. 1 plus 1 minus t squared on 1 plus t squared minus 2t on 1 plus t squared. I'm going to put a 1 on the top, it's getting messy. dx is 2 dt on 1 plus t squared equals, let's flip these around, these fractions. I'm going to get 1 plus t squared. I am working quite quickly through this, hopefully that is okay. 2 dt on 1 plus t squared. All right, cancels, cancels. Equals. Let's bring, I'll leave the 2 there. I don't know what's going to happen on the bottom. What have we got here? That's gone. 2 minus 2t is equal to 1 on 1 minus t dt, which of course is a log. We're going to have ln of 1 minus t divided by -1 plus c. And don't forget to substitute back in. We're going to have negative ln 1 minus tan x on 2 plus c. Question 12a. For real numbers a and b that are greater than or equal to 0, prove that a plus b over 2 is greater than or equal to the square root of ab. A couple of different ways to do this. I'm going to start, which I normally do, with this. X minus y all squared is greater than or equal to 0, which is a statement of fact. Now you can see this square root here. I don't want squares. I'm going to substitute in and say, well, that means that root a minus root b all squared must be greater than or equal to 0. Now let's expand. It gives me a minus 2 square root of ab plus b is greater than or equal to 0. So a plus b is greater than or equal to 2 root ab. Divide by 2 and we have it. 12b. Particle is moving in a straight line with acceleration a. The particle starts from rest at the origin. What is the position of the particle when it reaches maximum velocity? Maximum velocity, of course, occurs when a is equal to 0. So 12 minus 6t is equal to 0, t is equal to 2. But we want the position of the particle, so we're going to have to integrate. So a is equal to 12 minus 6t. Because we've got a t in this equation, we need to do dv dt. And so v will equal integral of 12 minus 6t dt is equal to 12t minus 6t squared on 2 plus c. All right, at t is equal to 0, v is equal to 0, so c will equal 0. And then again, dx dt is equal to 12t minus 3t squared. X is equal to integral of 12t minus 3t squared dt is equal to 12t squared divided by 2, so 6t squared minus t cubed plus c, resolving the constant at t is equal to 0, x is equal to 0, so c again is equal to 0. X is equal to 6t squared minus t cubed, and we want it at t is equal to 2. So 6 times 4, take away 8. 6 4s are 24, take away 8 is 16. And what have we got here? We have no units, so it's just 16. Question 12c. Particle with mass 1 kilogram is moving along the x-axis. Initially the particle is at the origin and the speed is, so initial speed is u meters per second to the right. Particle experiences a resistive force of magnitude v plus 3v squared. V is the speed of the particle after t seconds. The particle is never at rest. Show that dv dx is equal to negative brackets 1 plus 3v. All right, so F is equal to ma is going to be equal to negative v plus 3v squared. And we don't need to worry about mass because it's 1. So A is equal to negative brackets v plus 3v squared. Now we want dv dx, so we're going to use v dv dx, which is going to be equal to negative v plus 3v squared. And we can see how we're going to get this, can't we? Dv dx is equal to negative v plus 3v squared all over v, which is equal to negative 1 plus 3v. Hence, or otherwise, find x as a function of v. So we're just going to solve this differential equation, and we'll start by flipping it upside down. So do dx dv is equal to negative 1 on 1 plus 3v, and x is going to be equal to negative integral of dv over 1 plus 3v equals, so x, is equal to negative ln 1 plus 3v divided by 3 plus c at t is equal to 0. Initially the particle is at the origin and the initial velocity is u. So 0 is equal to negative ln 1 plus 3u all over 3 plus c. So c will equal ln 1 plus 3u all over 3. And joining that together, we're going to get x is equal to, let's bring the third out, and then we're going to have negative ln 1 plus 3v plus ln 1 plus 3u is equal to 1/3 ln, let's put this guy on top, 1 plus 3u divided by 1 plus 3v and hence or otherwise find x as a function of v. That is correct. 12D, using partial fractions, evaluate this integral, giving your answer in this form where f of n is a function of n. All right, let's start with 4 plus x. We're going to let this over x, 1 minus x in brackets 4 plus x squared. We're going to let this equal a over 1 minus x plus b over 4 plus x squared plus, we should consider that we might have cx over 4 plus x squared as well. All right, tidying that up, it's going to be equal to 1 minus x brackets 4 plus x squared. And we have got a outside of 4 plus x squared plus b outside of 1 minus x plus cx outside of 1 minus x. So we'll start by letting x equal 1, because that's going to wipe out this term and this term. We will end up with 5 is equal to 5a, so a is equal to 1. Now let's let x equal 0. So we've got 4 is equal to 4a, which is 4, plus in here b, and that's going to be 0. Therefore, b is equal to 0. That's nice. And then finally, it doesn't really matter. Let's let x equal negative 1. So 4 take 1 is 3 is equal to a 5a, so a is 1, plus b is 0, plus c times negative 1 times 2. What have we got here? 3 equals 5, take away 2c, 2c is equal to 2, c is equal to 1. And so, written in partial fractions, we're going to end up with, let me think what I'm doing here, 1 over 1 minus x, b is gone, and cx we need, plus x over 4 plus x squared equals, let's integrate, we've got ln of 1 minus x, divide by negative 1, I'll just put the negative out the front, plus, this is also going to be a log, I can see the derivative of the denominator sitting at the top except for that 2, so let's put the 2 in and adjust, and I'm going to end up with a half ln 4 plus x squared. All right, let's tidy this up before we substitute in. We're going to end up with ln, I'm going to bring this half up the top here, so that'll be the square root of 4 plus x squared, divided by, because of this negative here, 1 minus x, in between 2 and n, equals ln square root of 4 plus n squared over 1 minus n, take away ln square root of 8 over negative 1. Now remember, that's absolute values, so that's going to be equal to ln square root of 4 plus n squared, in fact I should have absolute values there as well, over 1 minus n, take away ln root 8 equals, let's join them together, ln, have a bracket there, we're going to have square root of 4 plus n squared over square root of 8, 1 minus n. Alright, we want this half out the front, so I am going to make this all into a square root like this. Big square root there, 4 plus n squared over 8, 1 minus n squared, which I might turn around in a second. So this is equal to ln 4 plus n squared on 8 n minus 1 all squared to the power of half, which is equal to a half ln 4 plus n squared on 8n minus 1 all squared. Is that it? Half ln a function in n, 8, and 1. Yes. Well done. 12e. Given the complex number z equals e to the I theta, show that w is purely imaginary. So z squared take 1 on z squared plus 1 is equal to e to the 2I theta take 1 on e to the 2I theta plus 1. Now I'm going to change this form. Instead of working in exponential form, I'm going to work in cis form. So this is cos 2 theta plus I sine 2 theta, but I'll bring this minus 1 over, plus I sine 2 theta divided by cos 2 theta plus 1 plus I sine 2 theta. Now I want to make the denominator real, so I'm going to multiply by the conjugate. So minus I sine 2 theta over cos 2 theta plus 1 minus I sine 2 theta. All right, expanding through the numerator, I'm going to bracket these two together. So I end up with cos 2 theta minus 1, cos 2 theta plus 1 minus I sine 2 theta cos 2 theta minus 1 plus I sine 2 theta cos 2 theta plus 1 minus plus sine squared 2 theta all over. The denominator is the difference of two squares, so cos 2 theta plus 1 all squared plus sine squared 2 theta equals cos squared 2 theta minus 1 minus I sine 2 theta cos 2 theta minus 1 plus I sine 2 theta cos 2 theta plus 1 plus sine squared 2 theta. Our objective here is to cancel out all the real terms, which you can probably see that that is already going to happen, because sine squared 2 theta plus cos squared 2 theta is equal to 1. Take away 1 is 0. And so we're left with a purely imaginary term. I outside of negative sine 2 theta cos 2 theta minus 1 plus sine 2 theta cos 2 theta plus 1 all over cos 2 theta plus 1 all squared plus sine squared 2 theta, okay, which is purely imaginary as required. 13a, prove that for all integers n, where n is greater than or equal to 3, if 2 to the power of n minus 1 is prime, n cannot be even. And I'm going to prove this by contrapositive. So a contrapositive statement still will be, if n is even, then 2 to the power of n minus 1 is not prime. Okay. Now let's start by saying, well, if n is even, we will let n equal 2k, and k is an integer. So 2 to the 2k minus 1, well, that's the same as 2 to the k all squared, take away 1, which is the same as 2 to the k minus 1, 2 to the k plus 1, which makes it seem like it can be factorized into two integers, which will make it not prime, providing one of these is not equal to 1, of course. But we know that n is greater than or equal to 3, and so therefore, because n is equal to 2k, k has to be greater than or equal to 2, doesn't it? So the least that k could be would be 1.5, but of course it can't be an integer, so the least it can be is 2. So 2 to the k minus 1, which is the lowest one, the least that this can be must be, the least that it can be if we put 2 in there must be 3. Therefore, both of these are higher than 1. Therefore, 2 to the 2k minus 1 is not prime. And so by contrapositive, we have proven the statement. Question 13b. The numbers an for integers n greater than or equal to 1 are defined as shown. The numbers satisfy the relation a squared n plus 1 is equal to 2 plus an for n is greater than or equal to 1. Use mathematical induction to prove an is equal to 2 cos pi over 2 to the n plus 1 for all integers n greater than or equal to 1. So we're going to start off by showing it's true for n is equal to 1. So this is the statement we're trying to prove here. So a1 would be equal to 2 cos pi over, and we've got 2 squared is 4. And cos pi and 4 is root 2 on 2, which is equal to root 2, so it is true for n is equal to 1. Now we're going to assume it's true for n is equal to k. In other words, that a to the k is equal to 2 cos pi over 2 to the k plus 1. And now we want to prove it true for n is equal to k plus 1. So we're going to start from our recurrence relation, which is here. So a squared k plus 1 is equal to 2 plus ak, which is equal to 2 plus 2 cos pi over 2 to the k plus 1, which is equal to 2 brackets 1 plus cos. Now here I want 2 pi over 2 to the k plus 2. Does that make sense? Because now I can rewrite that. Let me just write this in here for you. As cos of 2 lots of pi over 2k plus 2. And that is going to be equal to 2 cos squared pi over 2 to the k plus 2 take away 1, which I'm now going to make that substitution. Equals 2 brackets 1 plus 2 cos squared pi over 2 to the k plus 2 take away 1. These cancel, and I end up with 4 cos squared pi over 2 to the k plus 2, which is the same as 2 cos pi over 2 to the k plus 2 all squared. Now, if we have a look at this part here, a to the k plus 1, we want to prove it equal to 2 cos pi over 2 to the k plus 1, which is k plus 2. And so this thing squared would be equal to that squared, which is what we've proven. So therefore, true for n equals k plus 1, true for all n. 13c. Consider the equation z to the power of 5 plus 1 is equal to 0. Z is a complex number. Part 1, solve the equation z to the power of 5 plus 1 is equal to 0 by finding the fifth roots of negative 1. So we'll start with z to the power of 5 is equal to negative 1. And we're going to let z equal cis theta. And I'm going to rewrite this as cis theta to the power of 5. And on the right hand side, this is equal to cis pi. And you should know all of these. You know, if this is 1, then you put it equal to cis 0, if it's I, if it's negative I, and if it's negative 1. All right, so we have got cis 5 theta is equal to cis pi. And so we have 5 theta is equal to pi plus 2k pi, and k is equal to 0 plus or minus 1 plus or minus 2. And we're just going to substitute them in. I'll do one further thing. Divide by 5. Okay, when k is equal to 0, theta 1 is equal to pi on 5. When k is equal to 1, theta 2 is equal to 3 pi on 5. When k is equal to negative 1, theta 3 is equal to negative pi on 5. And k is equal to 2. Theta 4 is equal to, what have we got there? Pi. And when k is equal to negative 2, theta 5 is equal to 1 take away 4 is negative 1 take away 4, negative 3 pi on 5. Okay, so just up here, our solutions are going to be cis, and I'm going to put plus or minus in, make it a little bit easier, plus or minus, I probably still could put the bracket in, couldn't I, and pi on 5, cis plus or minus 3 pi on 5, and cis pi. Part 2, show that if z is a solution of this, but z is not equal to -1, then z plus 1 on z is a solution of this. Okie dokie. So let's start by, I'm going to expand this out. Oh no, I'm going to factorize it. Z to the 5 plus 1 is equal to 0. So this is the same as z plus 1, z to the power of 4 minus z cubed plus z squared minus z plus 1 is equal to 0. Now we know that z is unequal to -1, so we can divide both sides by that. We have z to the power of 4, take z cubed plus z squared minus z plus 1 is equal to 0. Divide everything by z squared. Gives me z squared minus z plus 1 minus 1 on z plus 1 on z squared. And now I'm just taking it up here. We're going to say z squared plus 1 on z squared minus z plus 1 on z plus 1 is equal to 0. Okay, we're nearly there. Just going to tidy this part up here because I don't want z squared plus 1 on z. In terms of that there, I want z plus 1 on z squared. So let's just expand this out up here. Z squared plus 2 plus 1 on z squared. So this down here is equal to, let me try and get this right, z plus 1 on z squared, take away 2, take away z plus 1 on z plus 1 is equal to 0, which is z plus 1 on z all squared. Take away z plus 1 on z minus 1 is equal to 0, and therefore satisfies this equation. Part 3, hence find the exact value of cos 3 pi and 5. So we'll start by solving this using the quadratic formula. So u will equal negative b plus or minus the square root of b squared minus 4 times a times c, or over 2a, is equal to 1 plus or minus square root of 5 over 2. So we've got two solutions, one which is positive and the other which is negative 5. All right, now we also know that u is equal to z plus 1 on z. So using this, we're going to have cis 3 pi on 5 plus cis 3 pi on 5 to the power of -1, which is cis 3 pi on 5 plus cis of -3 pi on 5. And expanding those out, we know those imaginary terms are going to cancel out. But we'll do it anyway. Cos 3 pi on 5 plus I sine 3 pi on 5 plus cos of -3 pi on 5, because cos is an even function, so that's 3 pi on 5. And then plus I sine of -3 pi on 5. Sine is an odd function, so this is going to become minus I sine 3 pi on 5. These guys cancel out, and we end up with 2 cos 3 pi on 5. So coming back up to here, 2 cos 3 pi on 5. Now we know cos 3 pi on 5, that's in this quadrant here, so cos is negative, so it's not going to be this one. It's going to be equal to 1 minus root 5 on 2. Therefore, cos 3 pi on 5 is equal to 1 minus root 5 on 4. Okay, that's it. In our final video, we're going to cover questions 14 to 16.